Hi there. Let's talk about electricity. We already learned that electrostatics means electricity that's just sitting there. Electricity in itself means that it can move. Okay, so what kind of charges do these atoms have? We already learned that this is an atom. Here's a proton. Here's an electron. There's a neutron. So these two things here make up the nucleus, and then the electron is floating around the outside. But this atom has a charge, okay? And what we look at is we add these together, one positive and one negative. What would that add up to? Neutral, these neutrons are worth 0. So that would be a neutral atom. This one, we've got 2 positives in the middle. These 2 are worth nothing. And then 1 negative. So what kind of a charge would this one have? When you add 2 positives and 1 negative, it would add up to a positive charge because it would have an extra positive in there. The next one, look at that one. Would it have a positive, negative, or a neutral charge? It would be a negative because there's only 1 positive and 2 negatives. So it has more negatives than anything. Okay. So static electricity, it is just sitting there. It's not flowing in a continual motion. That's a lot of static. Electricity refers to the flow of electric current in wires, motors, light bulbs, and other objects. So an electric circuit, when we talk about that, it's a complete path that electricity flows through. Here we have electricity that is flowing out of a battery. And this switch tells this to either let the electrical flow go through and light the bulb or not. Okay, when drawing circuit diagrams, we use these symbols. So a wire, like a wire that you would have connected in your electricity, is just a straight line. The battery looks like this. Here's the battery, the positive end of the battery, the negative end. The positive end is bigger because that's where the electricity is going to flow and start leaving the battery. We've got a light bulb, so that is what a light bulb looks like. The electricity will come in and then go out. We have a resistor, and that's what a resistor looks like, and a switch. This switch is open because there's a little doorway there. If it were shut, it would go that way. Okay. So here is a circuit again. Oops. And when you look, we've got the battery. The energy flows out of it. And then here's a switch. It's just like the switch that you switch on to turn your lights on in your house. Okay. So when we close this switch, it allows the electricity to flow. The circuit has no breaks. The electricity can flow freely. So the electricity goes out, flows through the wires, flows through the switch too because it's touching there, goes into the light bulb, goes up, follows this path, comes out, goes back, and then the negative charges go through, the electricity goes back through this negative end of the battery. And then it goes again. Ooh. And it keeps that light going, right? Okay, now what if we were to take that switch and pull it up? There would be a break in there, right? What do you think that light would do? It's just like this one. We all of a sudden stop the flow of electricity. Therefore, we can't get anything lighting it up. So an open circuit, there's a break in it. The electricity stops where the break is. Okay, inside a light bulb, follow the electricity, and where would it go? So we've got, here we go. The electricity comes in, boom. Did you know that it comes in? Well, it could come in down here too. Okay, so we'll say it comes in down here, right at the tip here. And it comes up. And it follows these little tiny wires. And then it goes through this filament. Oh, and then goes back down. And then it goes out. There is a little connection on the side where it screws in. It has to have this circular motion and then be able to be released. Otherwise, it would just blow up this light bulb. Now, these tungsten filaments, there's the name. It's the thinnest, tiniest wire. And the reason they used to make them so that the wire just went straight around like this. But it only, that much wire there, just one line of it, didn't light up a room very much. So they started coiling it till it came around. And that way more electricity is kind of put into that one area, and it lights that little wire piece up. Tungsten lights up when it gets hot with that electricity, and then we can see when it's dark. Okay, so electric current is measured in units of amperes or amps. You guys have probably heard that before. And a flashlight like this uses approximately 1/2 amp. I'm not going to quiz you on this later. I just want you to kind of know what an amp is. Okay, in a battery, the current flows out this positive end. The positive end has the plus sign, but also you can tell whenever there's a little bump on a battery, that's the positive end. And it flows out and then back into the negative end. Voltage is a measurement of the electrical potential energy. So you can measure the potential energy of a battery or the electricity going through your house. You can measure voltage by using this multimeter or multimeter. I always call it a multimeter or a voltmeter. You might have seen one that looks like this, maybe around your house, or maybe you've seen an electrician use one, or you've seen it in your physics class. The ones we use at school are sometimes red like this, but they're sometimes yellow too. You might see this. And then they've got these two, you can see these two little sticks here, and those sticks have two little pieces of wire there. And what it does is you let the electricity, you touch that to one end of the electricity and this to the other, and it flows through this little apparatus and then back out. And it will let the electricity still keep flowing, and it will measure it, how much the voltage is. So you can measure circuit voltage by inserting the multimeter into the circuit. So the circuit of electricity is just a circle, really. And then that electricity has to flow through this machine and give you the voltage. So here's the battery. You connect it up. Let the electricity flow. And then it lights up the light and it goes back into the battery. That is a circuit. It's making a circle. Okay, this guy, super important. He was born in Massachusetts in 1848. At 16, can you imagine at 16, he joined the Navy and fought in the Civil War. That's crazy. He helped Alexander Graham Bell make blueprints that helped Bell file the papers for the telephone patent. And of course, his name was buried deep, so because he was not a white man back then. So he improved the design of light bulbs by replacing the paper filament with a carbon one. This helped the light bulb to not burn out so fast. So here is the filament, goes up in, around, and then back out. You can see it in that light bulb, but they used to make them out of paper. And that paper, of course, would burn up and be done. And then they'd have to put more paper into that bulb, and it would just disintegrate again. And so light bulbs didn't last very long. And so he changed that into an actual piece of filament with carbon in it. And then it could light for a lot longer. And now we've realized, hey, tungsten is even better than that and makes it last even longer. So, science, we just keep improving things and learning more and changing as we go.